Okay, so here is an example for from the series things, sum of the given series. Okay, so we have to. This is the statement that the sum from 1 to n for this r is going to be half n into n plus one, and for all n where n is greater than or equal to one. Okay, so the first step will try to prove this for n equal to 1. That is your initial value. Sometimes, in some cases, this can be 0 over here. Okay, so right now the n is going to be 1. So let's see. This is when you have r from 1 to 1, and there is going to be r. So that is, that is going to be 1. Okay, and if you put this n1 here, this is going to be half into 1 plus 1. That is half into this 2 here. So that is equal to 1. So we have proved that, yes, this is true for n equal to 1. Now, this next step, step 2, you will assume that the statement it is true, uh, it is true for n equal to k. So this would become summation from R1 to n. This is going to be from 1 to k, sorry, because I have kept this n equal to k, and this is r here. So this becomes half into k plus 1. So this is our assumption over here, okay? I'm going to move into the third step, which is the most important step over here. So I have to prove that this is true for n equal to k plus 1. If I'm able to prove this, then this means that we have proved this by induction, okay? So this is basically your induction starts from here where you have put this n as k, okay? So you have inducted something into this statement here. So now this, your sum from R1 to k plus 1r, you guys can allow me to write it as r from 1 to k r plus this k plus 1. Yeah, do you agree with this step here? The sum from 1 to k plus 1 is same as from 1 to k, and then this is the k plus 1th term here. Yes? So we have already here that this thing is going to be half into k plus 1. This is half into k plus 1. And then I have this k plus 1. Okay, if you remember your trigonometric identities, when you're proving those trigonometric identities, this is really a handy thing to think about your right hand side, that what can be the form that you can have. So, you just keep your target in your mind that, okay, if you replace your n here as k plus 1, so this should look like as half into k plus 1 into k plus 1 plus 1, okay? So which can be also written as half into k plus 1 into k plus 2. So I have to make this thing, I have to bring this thing into over here, okay? So guys, can I take k plus 1 common from here? If I take k plus 1 common here, so I have half k plus 1, okay? And if I take the LCM inside here, you can see this will be 2 into k plus 2, and this would now become half into k plus 1 into k plus 2. And you see, we have got this thing. So I'll be writing this as half into k plus 1 into k plus 1 plus 1. So we have shown that this is really proving this true for n equal to k plus 1 as well. So we have done the most difficult part here. Now we have to write the statement. So um, when you're going to write the statement here, so you would say, okay, if you, just a minute, we have to write the conclusion here. So the conclusion would say that as our statement, as it is true for n equal to 1, and if you have to copy it down, okay, and if true for n equal to k, then it is true for n equal to k plus 1. You see, as it was true for n equal to 1, and if it is true for n equal to k, and we have shown that this is true for n to k plus 1, so this is going to be, so it is true for all n greater than or equal to 1. So that is how you will be concluding this. Okay, I have now one more example that is related to a work example related to how to prove by induction a divisibility test here, basically. So we're given a statement here that n cubed plus 3n squared plus 2, and we have to prove that this is divisible by the 6 for n is greater than or equal to 1. Okay, guys? So you see that our first step will always be that we'll try to prove for n equal to 1. So let's prove this for n equal to 1 here. So for this, I'll be putting 1 into this. This is 1 cube plus 3 into 1 square plus 2, and that is equal to 6. And you know that this, you can put a tick here that this means that yes, this is really true, that this is true for n equal to 1. Okay. Now, the second step, you have to assume here, let it is true for n equal to k. Okay, so this implies that this k cube plus 3k squared plus 2k, and let me suppose this as 6 x maybe. Okay, this is 6x, 6 times x. Okay, that means it is a multiple of 6. You can keep 6a, 6b, whatever you want. Okay, don't use this n or k again here. Now in the third step, we have to prove this. We have to prove it is true for n equal to k plus 1. Now this is where you will have to be showing your algebraic muscles here, guys. Okay, so this is k plus 1 cube plus 3 into k plus 1 squared plus 2 into k plus 1. Okay, so we simplify this. And when I simplify this, I have to expand all of them. This is going to be k cubed plus 3k squared plus 3k plus 1 plus 3k squared plus 6k. Please, guys, keep an eye. I might make a mistake here, okay? So if we made any mistake here, this will ruin all our working and waste a lot of time. Okay, so I have this thing in my mind that if I get something like this, I can change that with 6x, okay? So I have this k cubed plus 3k squared plus 3k. Okay, now let me split this. As I told you that you will have to be very clever algebraically. Can I split this 3k into 2k plus k? So this has been changed with 2k plus k. So I will be changing all of this with 6x. Can I do that, guys? This is 6x here. Okay. Now what I'm left with, I have here 3k squared. This is 3k squared. And then there's this k plus 6k plus 2k. That is going to give me 9k. Okay. And then I have this 1 plus 3 plus 2. That is going to be plus 6. Okay. So this is 6x plus 3 into k squared plus 3k plus 2. Okay? So now this is going to be, if we do some factorization here, this is going to be 6x plus 3 into k plus 1 into k plus 2. Okay, here you have to convince the examiner that look, this k plus 1 and k plus 2, these are going to be two consecutive integers. These are two consecutive integers, okay? So if k plus 1 is even, if k plus 1 is even, 3 into all of this is going to be, you will have to write this. This is going to be is divisible by 6. Obviously, an even number into 3, that will give you a multiple of 6, okay? And if k plus 1 is odd, then guys, can I say, then k plus 2 will be even. And in any case, this 3 into k plus 2 would now be equal to that multiple of 6. Okay? Multiple of, you have to write all of this, multiple of 6. So this means that this is also going to be, all of this is also a multiple of 6. And this was already a multiple of 6 over here. So this has proved, we have proved this by induction, that yes, this is going to be, this is always going to be divisible by 6 for n to be greater than or equal to 1. And never forget to write this statement correctly here. You have to say that as it was true, as it is true for n equal to 1, and if true for n equal to k, then true for n equal to k plus 1. Okay, so
Sir, I didn't understand
just
the last part.
let me complete. So it is going to be true for all n greater than or equal to 1. Let me pause this and then I can discuss this with you. Okay, now my
Okay, sir.
student is confused here that what am I saying here, this k plus 1, k plus 2. You see, you must have done these questions in your grade 7, 8 algebra, that the sum of two consecutive integers is blah, blah, blah. So if your first integer is x, the next one is going to be x plus 1. The very next is going to be x plus 2. So these are three consecutive integers. So, you know, these are two consecutive integers. So whenever you write the integer, like look at this 1, 2, 3 positive integers. I'm just writing the positive integers here, 1, 2, 3, 4, 5, 6. Okay, I was telling you there was a problem with the light here. So this is x into x plus comma x plus 1, x plus 2. These are consecutive integers with us. Okay, if I write here the integers 1, 2, 3, 4, 5, 6. Guys, if you just pick any two of them here, like for example, if I just mark these two, so one of them has to be the even number. Okay, so if there is let's say there is 3 times 4 times 5, so isn't this a multiple of 12? I mean a multiple of 6, sorry. Does this not have 6 as a factor? Yes or no? Hello?
Sir, can you please repeat? I didn't catch that.
If it is, if these are two consecutive integers here, 4 and 5, and I have, like, you know, there we had 3 into k plus 1 into k plus 2. And I was telling that these are two consecutive integers, like you have 4 and 5, okay? So this is 3 into 4 into 5. So isn't it a multiple of 6?
Yes, it is.
Yes, okay. And if instead you pick these two, okay, the first one is odd. So this is 3 into 5 into 6. These are, this number is still going to have 6 as a factor. So that is
Yes.
what I was telling there. I think I had something 6x plus 3 into k plus 1 into k plus 2. So all of this is going to be divisible by 6. That was the statement about. So I have a harder example here. Now the question says that the statement says that there is 9 raised to power n minus 1. We have to prove by induction that it is divisible by 8 for n greater than or equal to 1. I would like you to try this. You just pause and try this and then I'll explain. I forgot to mention this is divisible by 8 for all n greater than or equal to 1. So just try those 3 steps here and try to prove this. So I'll be going with you. You must have gone ahead. So the first step is you have to prove that this is true for n equal to 1. Okay, so this is going to be 9 raised to power 1 minus 1. This is 9 minus 1. That is equal to 8. So yes, we have proved that this is divisible, by 8 when you put n equal to 1. Now, then the next step, you will say, okay, let's assume, let's say, let it be true for n equal to k. Okay, so therefore this 9 raised to power k minus 1, and you just suppose this will be 8y. Okay, this is 8y. 8 times y is like 8 into anything is obviously divisible by 8. Now, the third step, that is a main step where your mathematics is tested. You will prove that this is true for n equal to k plus 1. Okay, so this now becomes uh, 9 raised to power k plus 1 minus 1. Okay, I'm stopping here. Okay, but you have to handle this. I want you guys to recall that when you have, for example, if you have 2 times 2 raised to power k, you can write it as 2 raised to power k plus 1. So you should allow me to write this back in this form. So we can write this as 9 times 9 raised to power k, and then there is minus 1. There is this minus 1. Okay. Now, from this relation over here, can I say 9 raised to power k is 8y plus 1? Hmm? So I'll be writing this 9 into 8y plus 1 minus 1. You see how smart you will have to be, okay? Now I'll be writing this as 8 into 9y because I have to show that this is a multiple divisible by 8. So I'm instead of 9 into 8y, I'm writing this 8 into 9y plus 9 and then minus 1. That is going to be 8 into 9y plus 8. So this is going to be 8 into 9y plus 1. So we are not bothered about what is inside the brackets here. We just know that this is 8 times all of this. So this means that all of this is divisible by 8. So this shows that we have proved, yes, that this 9 raised to power n minus 1 is divisible by 8 when you put your n as k plus 1. Okay, so now it's the time to write that conclusion here, that as it is true for n equal to 1, and if true for n equal to k, then true for n equal to k plus 1. So it is true for all n greater than or equal to 1. So now the next divisibility proof is that you have to prove that this 3 raised to 2 and plus 11 is divisible by 4. Try this, guys, okay? So I'm going to finish up to here, okay? Thank you very much for being with us.